Said we were going to end or start today with kind of the simplifications when it comes with structure. So you're going to do a lot of Lewis structures. In theory, you should be drawing these all out. And as you saw with the IR assignment, you're going to have to start to evaluate structures very, very quickly and readily. So some of the things like hybridization, how many bonds are there, charges, that kind of stuff should be coming very, very, very fast. Okay? So given an individual structure, you should be able to point that stuff out. Notice where there's inconsistencies, things wrong with it, that kind of stuff. Okay? A lot of the simplifications. So ultimately you go through all of the Lewis structures to then we back away from it and say, okay, well, we aren't going to spend that much time anymore on Lewis structures. And then we're going to go through a bunch of simplifications. So our first simplification is that we're dealing with fewer elements on the periodic table. So you get your hydrogen, carbon, boron, sort of, nitrogen, oxygen, and your halogens. We will see a few of the other elements show up. Sulfur will show up for concentrated acids. Aluminum shows up every once in a while, just not as often. All right? The next thing would be looking at shapes. So if we go back to our VSEPR theory, we're looking at much electron pair propulsion. We're looking at fewer shapes. Ultimately, everything is zeroed in that tetrahedral range. We will see a few trigonal planar objects show up, in particular in the case of boron and aluminum. But for the most part, we stay in that tetrahedral range. So being able to look at a Lewis structure and immediately come out what kind of shape you're looking at becomes really important. Okay? Push that a little bit further. Not only are you going to have to be able to recognize the basic shapes, but then you're going to have to see how those shapes relate to each other. Chapter 5 is all about three-dimensional structures and how those structures can compare. Do they overlap? Okay? Do they not overlap? Are they the same? Are they different? Okay? We'll go through those definitions on what those words mean, because ultimately they do change a little bit in organic chemistry. Hybridizations, we're only going to deal with up to sp3. Almost everything is going to be in that sp3 category. But just like with the shapes, we will see some sp2s show up. Okay, so you need to be aware of looking at a structure and immediately saying that is this hybridization. Okay? How is that going to have an effect on the overall atom? For instance, if I go through and take a look at methane, first off, what's the hybridization of that carbon? I was too slow. You got to go faster than that. Oh no, I was making stuff up. Hybridization on that carbon. That was a little slower. That carbon is sp. Okay. How does that change the properties of that structure? Ultimately, all we're looking at are carbon and hydrogen. Most people look at it and say, well, there's no difference between these. Right? The only thing that's really reactive is that pi bond. Turns out that hydrogen becomes exceedingly reactive when the carbon is sp, and not in the case of the sp3. Okay, well, why would that change? What else is changing with the hybridization?
Displacement of electrons.
Has to do with the balance of electrons and where they're existing. What happens to the carbon? If we take a look at the bonds that carbon is contributing to this. Okay, the orbital that it's supplying is an sp3 versus an sp. Why does that change anything? Okay, sp3 versus sp, which one has more S character? sp. More S character because there's less p in it. Okay? It's roughly 50% S character. What's the difference between our S and our p orbital? What's that? Energy, so we can look at sheer energy differences between those two. So if we're looking at more S character, what is that carbon going to do to the electrons in that bond? I like the hand motions. It's going to pull it in tighter, okay? Because we're trying to put those electrons in a lower energy. What does that mean? Is there some word that we can use to represent the ability of an atom to grab bonding electrons? Electronegativity. As we reduce the hybridization, i.e. going from sp3 to sp, we've now increased the electronegativity of the carbon. That is then going to really weaken that carbon-hydrogen bond, and that bond now becomes slightly acidic. Okay? So a slight change in the hybridization can make a dramatic change in the overall chemistry that we would evaluate. Okay, so you have to be able to look at it and say, yes, that is this hybridization, that is this one, and then be aware of those conclusions. Simplified drawings, when we go through and deal with our Lewis structures, every point will be defined as a carbon atom, okay, unless otherwise specified. So if we went through and drew out another structure in here, how many carbons do we have? We got 6 carbons. Right? It's ultimately just a laziness thing. We've decided that we don't want to specify that that's a carbon atom. So anytime that we have 2 lines intersecting, okay, we've got a carbon. How many carbons are in, let's call it a purple drawing, in that purple drawing? 2. Okay, we got a point at every end of the line. How many carbon atoms now in the purple one? 1. It's 1. What happened to that end point, which I'll kind of highlight as blue? It became the oxygen. We've specified it as the oxygen. Okay? Questions about that? Okay. Next big simplification that we end up going through and doing is with drawing out all these Lewis structures, we have some rules to go along with it. Those rules allow us to start to simplify our drawings. For instance, making carbons points, but then also implying hydrogens. Okay? We will imply hydrogens to our carbon atoms to satisfy the octet for carbon. So in the red, let's do the purple drawing. How many hydrogens are in that purple structure? Oh, you did count right. Dang it. We've implied 3 hydrogens off that end, and then we have the 4th hydrogen on our oxygen. Okay? I won't ask you the red one because I don't think I can count that high. Okay? So hydrogens will always be implied, and remember it goes to the octet. Right? So unless we see a charge, we need to have 4 bonds shown around carbon. If we don't see those 4 bonds, there's implied hydrogens attached until we saturate. Okay? The very last, or sorry, not the last one, the third rule on this is we will never, ever, ever imply charges. Okay? And the reason we can't imply charges is because we've implied hydrogens. We use hydrogens more frequently, so we'll imply those. Charges you must specify every single time. Okay? Which means you have to calculate it. There's multiple methods to go through and calculate your charge. All of it comes back to what we would refer to as formal charge. I gave you one method of it, or one version of that calculation back in the Lewis structures. But just to kind of reiterate, our formal charge will equal our valence electrons minus our bonds minus the non-bonding electrons. Right? This is a slightly different formula than you may have seen before. There are other methods floating out there. I've seen people go through and count, well, oxygen has 6, so I'm going to count 6, and then I have no idea what you're doing at that point. So if you ever try and calculate a formal charge, a different method, okay, and you get it wrong, all I'll end up doing is, see, I told you so. Okay? If you're right, I don't care. You can use any method you want. Okay? So make sure you specify those formal charges. And then the last one, which is particularly obnoxious and tricky, your nitrogen, oxygen, and your halogens will almost always have implied non-bonding electrons, again, to satisfy the octet. Okay, that one becomes exceedingly tricky. Usually, it doesn't matter, but it does become important when we look at those lone pairs trying to do some kind of reaction. Okay? So you got to kind of watch out for that and be aware of those limitations. Questions about any of the simplifications? Okay. What we're now about to bounce into is something that's not in your textbook, at least not in Chapter 1. They might bring it up later. We will see it for sure at the end of the semester, and we'll talk about it kind of periodically as we go through and do individual reactions. So what we're going to look at is our atomic versus our molecular orbitals. Okay? Hybridization, we ultimately waved a magic wand, and we said, okay, take these orbitals, and now we made new ones. And these new ones are our hybrid orbitals, and we just kind of ran with that, just kind of ignored the fact that that doesn't make physical sense. Okay? Physicists came back and said that's unacceptable. We have to go through and do this strictly mathematically. So they looked at how you could add and or ultimately subtract different atomic orbitals to make new orbitals. Okay? So what we're going to do is attempt to do this in a slightly more relaxed fashion instead of going into the strict mathematics of it, kind of make some general conclusions, and then look at the results of what happens when we make those conclusions. Okay? So if we look at our atomic, we've got our s orbitals. Okay? What was that shape? How did we define that shape? Okay, it's a sphere. How did we decide it was a sphere, though? Well, it has nothing to do with the electron count. Really what we're looking at is ultimately that center image. How did I make that image? It's the movement of the electron within a particular probability sphere. Okay, so what we're looking at is ultimately a wave. Okay? The path of that wave of our electron moving through that energy level. And at certain energy levels, it's confined to different spaces. That space gives us the s orbital. Okay? The reason we bring this up is we're bringing the concept of a wave to be able to manipulate some of these future drawings that we're going to look at. Okay? So what's the issue with waves? Okay, if we take a look at these two waves, okay, both of these are ultimately representing a very similar thing. We could even say that this is our s orbital. Okay? Is there something different about them? Inverse works. These are opposite phases. So that if I then added these two waves together, what happens? We don't even need a repulsion. What happens to the wave? It cancels. There's nothing left. Right? So if we take two electrons of the exact same phase, okay, or sorry, opposite phases, they cancel out. Okay, the cancel out doesn't mean we lose electrons, but what it means is that we now can't have electrons in that space. Those electrons are not allowed to be overlapped. So what are the electron clouds going to do? They're going to move to go the opposite directions. We'll see them existing in a different spot. Okay, what we would have generated is ultimately a node at that position where our waves overlapped. What happens? Okay, never mind. I thought I put up a different one. I didn't. That would have been nice. If they were in the same phase, what happens to the signal? Effectively doubles. Okay, so we see a larger space occupied by that. So if our electrons are in the same phase, they're nice and happy, and they will exist in that exact overlap. If they're in opposite phases, what happens? They don't exist in that overlap. They try and get away from it as best they can. Okay? We could look at this whole electron position with the square thing, and if you really went into it, I guess it can be interesting. Actually, that's a bit understated. I know it can be interesting, but we don't need to see that. Okay? So let's take a look at the bonding of a hydrogen molecule. So what we're going to do is take two hydrogen atoms, and we're then going to combine them in some fashion, okay, along this kind of thought process of looking at these waves to decide what could be the resulting molecular orbitals. Okay, so if we take a look at hydrogen, what's the atomic orbital we're going to be looking at for hydrogen? An s. Okay, and in particular, we could even get really fancy with it. We got a 1s. How about for the other hydrogen? Good? Or is, let's erase the dot, we got a 1s. Okay, so what happens when we make a molecular orbital? Okay, so let's look at, we'll call this our energy. We're going to bring these two s orbitals near each other. Okay, and let's push it to the extreme. Let's push them to the point where we think they would start bonding. You expect an overlap in the orbitals. Makes sense for the orbitals to overlap. Okay, so let's push to our nuclear distance. So we'll go ahead and put our nucleus in each of these. Whoops. Ignore that for the moment. If we did indeed make that bond, would we expect it to be lower in energy or higher in energy than the atomic orbitals? Okay. If it's higher in energy, would we ever make the bond? No. Where should our bonding orbital be? If we actually get a new bond to occur between these two atoms, where should that molecular bond energy be? Lower in energy than our atomic orbitals. Otherwise, there's no reason for our atoms to come together. Okay? This is irrelevant on whether or not there is a bond. We're just saying, if there is a bond, it makes sense for it to be a lower energy state. Okay? So if we drew that out, we could now draw on our nuclei, okay, for our two hydrogens that are now close enough to each other. And we could then go through and draw in our spheres. Horribly drawn, but you get the idea. Okay? Close enough that we get some kind of overlap between them. Okay? What happens if we think we bring these together and we don't see a bond? Should that be higher or lower energy? So now we've fixed our nuclei at these exact positions. We're saying you now decide nuclei. Is it a bond or is it not a bond? Okay? Those are our only two options. If it's not a bond, where should that energy be? Should be higher in energy. Okay? So we could go through and draw something similar, but now at a higher state. Okay? And I'm going to copy this at the exact same, but we'll change this in a little bit. So if you don't like erasing, you might not want to draw. Okay? So what we're effectively saying is that as we bring these atoms near each other, we can either progress down towards a bonding orbital, or we could progress somewhere upwards towards a non-bonding orbital. Anybody heard of this in 151? Maybe one or two of you. Well, we're looking at the linear combination of atomic orbitals, molecular orbital theory. Okay. What kind of bond did we form at the bottom? Okay. We did talk about the two bond types. What were the two bond types? Sigma and pi. What was the difference between them? Sigma was looking at single bond. What else? Some type of s orbital. Okay? It could be sp, sp2, sp3. If we have any s, we're looking at a sigma bond. Okay? So what we've got down at the bottom is, whoa, double whoa, everything's going wrong. We've got a sigma bond. Okay? And we can use that little sigma. One of the other big characteristics of a sigma bond is something known as direct overlap. Okay? We've got this space in between where the orbitals directly overlap. What happened with the p orbitals? Or, sorry, when we formed a pi bond, what orbitals did we use?
P orbitals.
We used our p orbitals. And what happened with the overlap? Okay, it was an indirect overlap. It was our p orbitals being parallel to each other that allowed them to kind of quantum mechanically jump from space to space. We didn't get a direct overlap. Okay? What happens as we look at our upper energy level? Okay, is that one best described as sigma or pi? What orbitals are we using in that top one? Still an s orbital. Okay? So we are still looking at a sigma type bond. But is it a bond? No. So we end up giving it a sigma star or antibond. Okay, so let's push this a little bit further. We said our electrons moved in waves. Okay, well, anybody see the wave in the circle? A little bit difficult to see. So let's look at our wave and kind of graphically interpret it. We'll draw this up a little bit higher. If we look at our s orbital, we're going to end up with two possible waves. Okay? Let's color them in so we can now express. We've got two s orbitals. One is our shaded wave. One is our empty wave. Okay? Those are our polar opposites. How is that going to affect our results? Okay, if we now go through and take that information into our sigma and our sigma star, or anti-bonding and anti-bonding, what would be the best way to represent my bonding shape? Would I expect those orbitals to be the same phase or opposite phases? Same phase, because in the bond, where are the electrons? in between the two atoms. So I would expect in my bonding orbital to have the exact same phase on both orbital lobes, which means I get that positive overlap. If we go through and instead of looking at this as just kind of these orbitals, we could now propagate this out into actually kind of describing what the actual shape of our orbital would be. What are the odds of finding an electron on the far left outside that last nucleus, somewhere over here? Not very good. So we want to use, again, our shape ideas to represent this. What are the odds of finding our electron somewhere in the middle? Pretty good. So what we end up seeing, something along those lines. Very low probability for electrons existing on the outside of our bond, very high probability for existing in the middle. Okay, if we wanted to, we could even shade this in, but I don't feel like coloring today. All right, what happens with our anti-bonding orbital? We don't want them occupying the space in between. Okay, and we know that because our phase is now out of alignment. One of them is shaded, one of them is not. So where they overlap, we cannot have any existence of an electron. So what we've effectively got is a nice little dotted line to help me draw. And what we're going to say is that we're going to have electron density on the outsides. But at this point, our phases look the same, so we can now color them in. We have opposite phases in our anti-bonding orbital. And if we look at our drawing, how much electron density is found between the nuclei? None, which means no bond or an antibond. Right? This is what that linear combination of atomic orbitals is attempting to do. It gets a lot more complicated. We're going to try and keep with it on the simple level, at least as simple as we can deal with. Okay? Questions about this one? Because the next step up is going to involve what? P orbitals. Okay, so it's definitely going to get more complicated. And I forgot to use digital renderings, so I'm going to have to deal with my crappy hand drawing. Okay, so questions about this? Okay. What happens when we move to a situation where we could look at p orbitals? Now we got nitrogen. Okay? I'm going to ignore our s orbitals. Why would I ignore the s orbitals? We already did it. Okay? We know what those look like. Okay? So let's look at our p orbitals to see what can happen with those. We end up with how many p orbitals? I might have to draw that a little bit lower. We get 3 p orbitals. Here's the one that's going to be crappy, but okay. And we could go through and do the same idea on the other side. Are you laughing at my p orbitals? Okay. What happens as I bring these near each other?
Depending on how they're oriented, you're going to either repel or attract.
Depending on our orientation, and I would avoid the repel and attract at this point, because regardless, that's going to happen for every single one of these. Okay. But depending on the orientation, we're going to change the type of interaction. Okay. So for instance, let's take, just for the sake of argument, that one with our blue lines underneath, and that one. Would I expect those two orbitals to interact with each other? Why not? They're not in the proper orientation to overlap. Orientation is critical when looking at bonds. Okay, so let's switch that up, and instead of the first and our second, let's do the first and the first. Parallel, we might expect an interaction between those two. So if we drew those out, we'll label those as blue. Okay. If we formed a bond, we would expect a lower energy, right? So let's draw out a little bit lower energy. Okay. One of the things that's interesting with p orbitals is p orbitals are not as simple as our s orbitals. What makes them slightly different? Oh, I actually shaded that one already. What's special about our p orbitals? They have different orientation and they start with different phases. Okay? Each lobe has a slightly different phase or has the opposite phase. Right? So when we go through and look at our bonding situation, what would we expect our phase to be between these two p orbitals? Right, I'll start with this one. Where would you expect the next one to be colored in, top or bottom? Top, because matches the phase. We could now get that electron jumping across. Right? What happens? Call it purple now. Let's take a look at these two interacting with each other. What happens now? So with our first pair, took two p orbitals, okay, thumb and pinky, we brought them near each other, now they can do their interaction. What happens when we look at the purple ones? What's the orientation? Now what happens when I bring them near each other? Don't even look at repel or even phases yet. We get a direct overlap. What type of bond do we generate from a direct overlap? We're looking at a sigma overlap versus the pi. Okay? If we propagate this out into a whole lot of other things, particularly with your nitrogen and oxygens, we have to then evaluate different energy levels of each of these. And I'm not positive, but I'm pretty sure our sigma in this case drops to a lower energy. Let's see if I can draw this. Okay, it's a little crooked, but you get the idea, right? So now we got to decide, what do we expect of our phases? I want to color this one in here. Should I color the next p orbital left or right side? Why left? Getting the same phase to generate that bond. Okay. What happens when we move to our very last example? Again, we started thumb and pinky vertical, then side by side, then kind of away from us. When we bring them in together, what kind of overlap do we start to see? We start to see the pi overlap, an indirect overlap. They are parallel p orbitals. This is going to be awful to draw. Do we already have a p orbital overlap?
Yes.
Is it different in energy than the one we're looking at now? No. They're all p orbitals. Okay? And it's the exact same type of overlap. So what we end up generating, hey, this will work nice because I've already started shading it like that. Okay? Our parallel situation. We're still in phase on that back and front end. Okay? What happens if we look at the opposite? If we look at our anti-bonding situation. Okay, let's take a look at our sigma interaction first. If I shade here, what happens on the other side? Left or right? Right, so they are now out of phase of each other. If we look at the pi, I'm just going to draw one of the pi's. Top or bottom? Okay. Again, out of phase. What does this end up doing as far as our energies? Well, number one, it tells us how these orbitals need to arrange to generate bonds or not bonds. Okay? Really, really important when we move into the very last section for this semester, our Diels-Alder reactions. Okay? Right now, I want you to be aware of it because what happens if, for instance, I take a look at a new rendering of that bottom one, okay, and I want to draw that orbital a little bit better. Look at the nucleus. Where's most of the electron density? In between. But I also still have little nodes on the outside. And we could shade everything in the middle. What happens with our top one? Okay. Why has this become important? I can start to find ways to shuttle electron density in. If I can bring in another species that happens to have an orbital of that same type of overlap, I can start to form a new bond or break the anti-bond in my original structure. Okay? So we will come back to these kind of drawings. I could, considering doing more, but I don't think I really want to unless there's questions. Do you guys have any questions about it? Hi. We'll do one quick example, let's do something a little more polar. We looked at a carbon-oxygen. I want to take a look at the overlap of two p orbitals. Okay, and we're going to do what I'm going to label as the px. What would I expect the overlap to look like? So our first pass, we're going to go lower in energy, right? Oh man, it's getting ugly. If we shaded it, we would expect the same shading. If we propagate this now into kind of doing the addition of these two orbitals, what would it look like?
The most of density would be between
Okay, so we might predict that most of our electron density, whoops, sorry, that got a little ugly in there, would be in between, very little on the outside. Should it be nice and symmetrical? Why not?
Because they're different weights or atomic masses and electronegative.
The electronegativity. Where is the bulk of the electronegativity? On the oxygen. So we would expect a lot more electron density. I didn't do a very good job drawing that. Towards our oxygen, and very little on our carbon. What does that start to mean the carbon wants? Electrons. Does it have the beginnings of an empty orbital on the other side? Yeah. So we could bring in something else. Horrible example, but something like chloride. They could start to share electrons and push the electron density all the way over onto the oxygen. Okay, completely breaking that bond. Okay? Questions about that? So periodically you will see me draw molecular orbitals. Okay? Typically we'll see the p orbitals. You might see some of the sp hybrids, particularly when we get into the reactions and how we can get the bond overlaps to generate new bonds, okay, and to break old bonds. Okay? Questions? Okay, I just thought of another question. What else changes as we go through and look at our bonding versus our anti-bonding? Someone actually used the key word. What electron density is between the nuclei in this example? Or at the nuclei? Is there any electron density at the nucleus? No. So what we've generated is two spots of 0 electron density. What we've got is referred to as a node. How many nodes are in our bonding situation? Move to the anti-bonding, what happens? And right through the middle, we have another node. What happens as we increase the number of nodes?
less bonds.
Could look at less bonds, that's a stretch though. What else changed? We went from the bonding to the anti-bonding. Bonding down here, anti-bonding up here. Energy. Okay? As you increase the number of nodes, what happens to the energy? It gets higher and higher. Okay? So what we're looking at is we want the minimum number of nodes, the minimum number of places where our electron is not allowed to jump. If we can get it so our electron can jump all the way through, we've delocalized the electron. We've spread it over a larger area. What does that do to its effective charge? All right, this is a fun example. Let's take a look at this shape versus this shape. Well, let's be a little bit more dramatic. Why not? Still not small enough. Okay, let's take a look at a single electron. Okay, so our single electron, there's our dot for a single electron. We're going to put that electron into each of those spaces. Okay, what can you tell me about an electron? Is it stable? No, remember the fork in the outlet? It hurts, right? Okay, so here's your option. We're going to put an electron in there and an electron in there, roughly the same size. You now have to stick your hand into it, to either of those. If you hit the electron, it hurts. Which one do you stick your hand in? Why the bigger one? Less concentration of that charge. We have delocalized that electron and its effective charge over a much larger area, which means what happens to the overall effect of our charge? Gets smaller, gets closer to neutral, which is where almost all of our reactions are going to end up, trying to drive to that neutral state. Okay? So when we look at our molecular orbital theory, what we're trying to do is, again, always drive to that lowest energy state. We want the place where we can get the electron moving as much as possible. Okay? Questions? Okay. We will come back to it when we look at breaking bonds and making bonds. When we're looking at pushing this forward, how did we decide where our electron density was located? I remember when we looked at the example of our carbon and our oxygen. Where did we decide to put most of the electron density? Put most of it on our oxygen due to that electronegativity. Is that going to change the reactivity? Yeah. That oxygen now has a lot of electron density, making it fairly negative. What does it want to react with? Something positive. Carbon just lost a lot of electron density, which means its charge starts to become positive. What does it want to react with? Something negative. How do we decide that again? Electronegativity. Right, so we're going to keep coming back to electronegativity because it's really the root of how we generate different functional groups. Right, so what we end up doing is taking the number of elements that we're working with, those 10, and we combine them in a variety of fashions. If in the process of that combination, we generate some drastically radical new reactivity, one atom becomes massively more positive than it was in any other combination, we now want to label that and say that is now going to react differently. So we end up giving it different names, and that's ultimately where functional groups come from. We looked at how those different arrangements of atoms changed the chemistry enough, we gave it a new functional group name. Okay? So what we're looking at is the balance between these. If something's very electronegative, it wants to balance out that charge, right, by sharing those electrons with something else, at least as a first approximation. Okay? So if we find something very negative, we just now need to find something that's very positive and put them together. Which do you think would react first? If I have something really negative, is it going to react with the most positive or the least positive? The most positive. Okay? Second semester, that's all second semester is. Okay? Except it's actually a little bit more complicated than that. It's not, here's one negative. It's, here's 4 negatives. Here's 4 positives. Find the most in each and pair them. Okay? And then propagate it like 6 times after. First semester, thankfully, we kind of sit with just kind of that one. Here's something positive. Here's something negative. What can they do? Okay? So our overall functional groups. Remember the list of our atoms that we can work with. We can look at sigma bonds, so hydrogen being bound with any one of our other elements, and we end up generating new functional groups out of it. Okay? We can look at alkanes or alkyls. Why did I not specify alkane? Or did I leave it as alkyl for that first one? What's an alkane? Just looking at carbons and hydrogens, nothing fancy, right? There's an alkane. Has a carbon and hydrogen. Heck, why not? Let's go ahead and highlight it. Still have that carbon to hydrogen single bond. Is that still an alkane? No, that's now an alkene. Okay, so you got to be a little bit careful on where we specify these bonds. That's why that one's labeled as an alkyl. Carbon to nitrogen, we're looking at an amine. Oxygen to hydrogen, we're looking at a hydroxy. Okay, why did I call it hydroxy and not alcohol? Okay, if we go through and take a look at that one. This one's popular. So what's this called? Ethanol, usually one of the more popular organic compounds. Okay, what happens? We got our OH, right? Let's go ahead and highlight that in blue, nice and 3D. Do I still have my OH? Is there still an OH there?
Yeah.
Yes. If we're referencing just the OH, that is a hydroxy. If we're referencing now the chemistry associated with this new arrangement of functional groups, is the chemistry drastically different of the OH? Yeah. We started with an alcohol, and now we have carboxylic acid. Any guess it's how it reacts? Donates the hydrogen and acts as an acid, hence we call it a carboxylic acid. Okay? So the intent behind these kind of lists of names is the simplest functional group. We can then combine these in a variety of fashions. If we again go through and look at our sigma structures between carbons and all of our elements, we can end up with more possibilities. We can look at our pi system. We do carbon-carbon with pi's or nitrogens. We again change that functional group. We get a slightly different name coming out of it because the chemistry changes. Right? What happens if I now take these kind of first order functional groups and start to string them together? If I take, say, a carbon-oxygen double bond from our carbonyl and put it near that alcohol, or that hydroxy, sorry. We now change again the functionality. So we get a first order pass of functional groups of just atom to atom. Then we take a second order pass where we then start stringing together multiple different functional groups, and that can have an effect on the overall functionality. Okay? That means you'd be responsible for all those possible combinations. Lucky you. Okay, thankfully, we're going to simplify it a little bit. Your textbook probably has a far greater, we already talked about why different names, several combined. Kind of a summary of all of our functional groups. These are the ones that you will see in a year of organic chemistry, okay, that you're responsible for naming and being able to interpret all of the chemistry with. Remember, this is a year of chemistry. We aren't learning all of these this semester. Any idea what we're learning this semester? It's really centered just on that first column. The second two columns are pretty much second semester. So a lot of chemistry shows up. Okay? We will start to see the alcohols show up, the ethers. We will probably see the amines show up as well as kind of side effects. Okay? But what we're going to be primarily concerned about is that first column and how each of those individual functional groups react in different situations. Okay? So I would highly recommend that you spend some time and actually get these memorized because I will make reference to it. So if I say an ether functional group, you should know immediately what that entails as far as the structure goes. Okay? Why is it important to know that?
How it reacts.
It's going to determine how it reacts. Okay? So one big thing that you'll find out, is it my next slide? Yeah, it is my next slide, is nomenclature. How do we name and put these things together? Okay? As we progress through the semester, you will find very, very quickly that I am horrible at nomenclature. The only things I know how to name are because people have asked me how to name. So I am forced to then look it up and learn it. I never spent the time to memorize it. All right? Nomenclature is really only important when talking about organic chemistry, which is one of the reasons why we go through and make you memorize your functional groups. Okay? The memory behind the functional groups, as far as I'm concerned, is because if I want a quick question and ask about the reactivity of alcohols, you can immediately translate alcohol into a structure and tell me about the reactivity of that structure. It simplifies what I end up having to do. Okay? If instead we do it based on ultimately how you'll probably end up learning it, looking at the structure every single time, you'll be able to understand how to draw things, react those individual structures, but you can't talk about it worth crap. Okay? Which arguably isn't all that bad. Okay? Why might that not be that big of an issue? When you take your final, you better not be talking through it. Okay? All you have to do is be able to read the questions and answer those questions based on it. You will be asked questions about nomenclature. The ACS test, in my opinion, is not particularly nice in that fashion. They will ask a question where they give you the name, but ask something about the chemistry. It tests two things. Do you know your naming, and do you know the chemistry? Okay? So be aware you will have to kind of interconvert between them. It takes practice to get used to the nomenclature, but it's not that big of a deal. Okay? So get your functional groups worked on now. These are pretty much everything that you will see in the course of a year of organic chemistry. Simplified the rules all down into pretty much one big slide. This is not 100% perfect, but it gets most of your nomenclature down. All right, so you would identify individual functional groups. How do you name those individual functional groups? Okay, for instance, we looked at ethanol on one of the last slides. Right? What was the functional group in ethanol? Anybody remember the structure? What functional group is in this? We've got the hydroxy, or our alcohol. How do we name our alcohols? Well, we name it as we would normally, and then at the very end where it has an E, we substitute OL. So in this case, what we've got is a linkage of 2 carbons. What is the name for 2 carbons? Go to our number of carbon lists. 2 carbons gives us F. What kind of connectivity do we have between our carbons?
Single bond.
Single bonds, suggesting which functional group? Alkanes. How do we name our alkanes? We just add the ane ending. So we would have ethane. What do we do to finalize? Take the E off the end and make it an OL. And we end up with ethanol. Or if you remove the pronunciation weirdness, ethanol. Okay? It requires ultimately coming back and forth between a variety of different things. The most important part for you guys to be able to nail down is going to be the number of carbons. Okay? So we don't call these 2-ane or 3-ane or 4-ane. Those actually sound kind of cool, but we end up going through and using our Greek prefixes. So you need to know what the Greek conversion is for each of those numbers. Okay? So you're responsible for those. 1 through 6 you will see super frequently. Absolutely, back of your hand, immediately fast, you know that. The 7 through 10 took me a while. You just don't see them quite as often. They do show up, but you just won't see them quite as frequently. Okay? So start working on getting that information memorized so you can start to do that translation very quickly when we get into that translation, which is chapter 4. Okay? Questions? Now remember, you're not strictly responsible for nomenclature yet. So what happens when you see a name in your homework? Thank you. Okay, your homework is on the internet. Google that name and get that structure. Okay, you might take an average of possible structures just to make sure you're not being misled somewhere. Okay, so make sure you find a consistent structure with it.
I have a question.
Yes.
What do you mean by priority of naming functional?
So the priority of naming functional groups. What happens if you have multiple functional groups in your structure? For instance, with ethanol, how many functional groups do we technically have according to this list? We have 2. We have alkane and alcohol. Which functional groups takes priority? The alcohol, that's why it's higher on the list, which means the suffix that we use, the very end, is going to be based on our alcohol. Okay? So as you move through the semester, you're not going to end up with just one structure, an alkane and say one functional group. You could very well end up with 6 different functional groups in a single structure. You have to be able to label all of them according to the priority list. Okay? Again, I hate nomenclature. So most of the questions you'll get from me are going to be relatively simple. Okay? To give you an example of how much I kind of hate nomenclature, when I took organic chemistry, this is a fun little story. Any ideas what my grade was the first semester? W. I withdrew. I was very, very failing first time around. Okay? Second time around, I took a look at the material and said, this is a load of crap. I need to figure out a better way to go through and do this. So instead of looking at my grade, I looked at the material. What did I think was most important? Okay, well, organic chemistry, in case you couldn't tell about how we've discussed it so far, is all about how different atoms interact with each other. Well, when you're given a test on a question, what are you given? Those different atoms. You're given that structure. So what I decided was most important is how to interpret the structure. What is that structure doing? What can it do? Okay? Nomenclature is all about how we talk about those individual things. So when it came to my ability to speak about organic chemistry, I've improved a little bit, but not that much. Pretty awful. Okay? And I decided that I was going to spend exactly 0 time studying nomenclature. So what happens when you see a nomenclature question on a quiz?
You cannot answer it.
Didn't answer it. Okay? Turned out nomenclature made up roughly 10% of the grade, which meant I ended up with like an 88% in the class. If I had spent just a little bit more on nomenclature, I probably would have gotten an A in the class. But I didn't. That was a conscious decision on my part to understand what the chemistry was that was happening in the reactions. So I gave up on nomenclature entirely as a part of the course. Along those lines, I don't want to cheat somebody else out of the potential for getting an A when it comes to nomenclature as well. Nomenclature is an important part of the class. It is not going to be 10% of your grade. Okay? You'll probably see it hit about 5% of every exam, maybe 6 or 7%. Okay?
In the homework, you need
In the homework, it's going to show up, but we've already discussed how you avoid nomenclature in the homework. Google. Okay? So the practice will build your naming ability. That is the only way I have learned how to name. Okay? It's solely based on practice. Okay? Why do I find naming a bit obnoxious? Okay? When we look at how a reaction works, it works because of, I'll come back to you, the structure, the electronegativities, how those things balance and interact. Where does nomenclature come from? Where does nomenclature come from? Yeah. Nomenclature came from a bunch of old guys, probably white guys, sitting around a table saying, this is how we are naming it, period. Anything that differs from this is wrong. Okay? There's some logic to it. There's some sense behind it. But as you will encounter multiple times, there's plenty of cases where it's just like, what the heck were you thinking when you tried to come up with this naming system? Okay? That said, push into biochemistry, they really don't know how to name. Okay? They just make stuff up and make everybody memorize it. We at least have an organization behind the naming system. You don't have to like it, but at least there's rules. If you follow those rules, you're right. Okay? So, if you've got questions about naming, I will refer you probably to the textbook first. But I will still try and help you as much as possible too. Okay? Try and get you some of those rules down. Mostly when you're looking at your ACS test, you're looking at the simple general rules. This slide, I think, covers everything that you would possibly see as far as the ACS test and naming goes. Okay? You might have to do some process of elimination, but it would get it there. Okay? Questions? Okay, I waited longer that time just for you, so I didn't talk over you. Okay, so let's actually make this interesting now. Reaction versus interaction. I know, because everything else was so interesting. How could it possibly get more interesting? Okay? Before a reaction can occur, we must have an interreaction. There has to be something to connect these. Okay? So I've got an example of 4 different types of bonds up here, and what we're going to try and do is derive our intermolecular forces. Ridiculously important, Okay? You need to understand your intermolecular forces, and you need to understand where they're coming from to be able to do a lot of the chemistry we're dealing with. Okay? So let's start with, let's go with sodium chloride. What type of bond is there? Let's back off of that. It's an ionic bond. Okay? So we now have this quote-unquote molecule of sodium chloride. And now what I want to know is how is it going to interact with another molecule. And we're going to go as simple as possible. Let's have it interact with another molecule of sodium chloride. So what I've got here are two examples. Okay? We can have our chloride interact with the next sodium, or we could have our chloride interact with the next chloride. Which interaction is preferred? Top. Okay. Good job. You're absolutely correct. Okay, why? Getting at good ideas, electrostatic attraction helps out, electronegativity helps out. Okay, but let's really set some rules into this. Let's really work with something. To do that, we're going to make this a lot more difficult. Let's take a look at the next one down. Which interaction is favored, top or bottom? Ooh, it's kind of like, oh crap, what happens now? You guys picked up the sodium chloride just fine. Okay, what's going on with the carbon hydrogen? Why do you not see a favoring here? What's that? So bringing bonds into it is an interesting idea, but can't look at bonds. All we're looking at is an interaction in this case. There is no bond breaking, there is no bond forming. Okay, let's propagate this out to these. If we now go through, take a look at our interactions again. What we're trying to do is come up with some way that we can predict these consistently. So we can label all, well, I'm going to change the color on that. Oop, no, I'm going to change the color on the other one. The color changing might make sense if I can get through this. We're done at 12:30? Okay. You can't change the clock on me. I've been started on that clock. Okay, so we've got these interactions. Okay, that first one you guys had right away. So let's take a look at that one. Why is that top one favored? Told me electrostatic. I had no idea what that means. Told me electronegativity. I kind of know what electronegativity means, but that's not a bond, so that doesn't work. If we look at the bond between the sodium and the chlorine, there's a large difference in electronegativity, and that chloride becomes negative charged, and the sodium becomes positive. What type of bond do I have in that sodium chloride? Same situation. I get positive, negative. And in the bottom case, same deal. Why would I favor the top interaction? Partial positive, or it's actually not partial, formal positive and formal negative. Why is that important? Charge is bad. We want to neutralize that charge. So when we look at the interaction, we're looking at those two things interacting with each other to cancel that positive and cancel that negative charge. That's why we see that top one. That bottom circumstance does what to the charge? Anything, it just makes it more negative. Okay? That does the opposite of what we really want to do. We want to drive towards lowest energy. Okay? So let's take a look at our green one, which I'm going to make orange just because I don't think I can see the green one on the screen. Which interaction is favored now, top or bottom? It's still the top. Okay, why? Oxygen is more electronegative than hydrogen. So I did hear a negative there, which means our hydrogen would be positive. And I'm going to challenge you and say you're wrong. Oxygen is not negative. Hydrogen is not positive. Those are not proper formal charges.
Partially.
They are partially charged. We have to come up with a new notation. Okay? Otherwise, what we're saying is this oxygen is equivalent to the chlorine, and that's not the case. Okay? That chloride is definitely negative. The oxygen is not formally negative. So how can we adjust the notation? Everybody has fun descriptions for this letter. Squiggle, common. Delta. What does delta mean? Change or a difference. We're looking at a change or a difference between the charge. Okay, so we're looking at those partial negatives and partial positives. That same partial negative and partial positive translates up to our oxygen. Or sorry, our other oxygen and hydrogen. Why is our top interaction favored? Again, we're trying to diminish that charge, neutralize that charge. Okay? What happened in our very last case? By very last, I mean our carbon hydrogen, the last one that's actually on there. Okay. What's the difference in electronegativity between our carbon and hydrogen? How big is that difference? It is so small that we define that bond as nonpolar covalent, which means what charge builds on the carbon? Nothing. What charge builds on the hydrogen? Nothing. What kind of interaction am I going to get between nothing and nothing? Lack of a better descriptor, nothing. Okay, so we end up not seeing an interaction there. Okay, at least as a first pass. Is that true? No, and you know that because Chem 151, what section Chem 151? Step away from intermolecular forces because that's all we're doing here is defining them. Why is that force existent? We just described that that shouldn't have anything. What's that? We could propagate something all the way out there, but even then we would think that we don't have those charges, we shouldn't get an interaction. Where does this interaction become really important? Well, okay, that was a dumb question because it's really important everywhere. Gas laws? You looked at the ideal gas law. Why is it ideal? What's an assumption that allowed it to be an ideal gas law?
It's a standard temperature.
What were our perfect conditions? No two particles interact more than bouncing off of each other. If there is an attractive force between them, what happens to the ideal gas law? It fails. So one of the things that you should have talked about in 151 was the real gas law, or a version of that real gas law. Who discovered that real gas law?
Sir, real gas.
Van der Waals. The interaction we're looking at here is a Van der Waals attraction, named after him because, at least at first pass, we would say it's irrelevant. Turns out it is pretty relevant. Okay, he was the one that proved it was relevant to look at. Okay? So we need to come up with ways that we can now predict when these interactions are going to show up. Okay? And actually, even before we get into the predicting part, are these interactions different from each other? Okay. Determine differences. This is organic chemistry. Remember, we're looking at energy. So how strong are each of those interactions? If we compare purple to red, is there a difference in energy between those? Yeah, there's a massive difference there. Purple, we said, was nothing to begin with. Okay, red is going to be really big because we're trying to neutralize those charges. So we're going to get a very strong attractive force up in our red situation. And in our purple situation, we're going to get very weak. Okay, well, what about our orange one? Just because you didn't say middle, I'll say middle. Okay? See, you were wrong. It was middle. Okay. Somewhere in our middle energy between these. Okay, so we want to be able to predict so that when we look at a bond, we can identify what type of interaction is there. And why does that become important? Well, if I can identify by looking at that structure that it's going to react really strongly, that means I should focus all of my energy and thought process on that one section and not somewhere else where I get a very weak interaction because there's no weak attraction between it and something else. Okay? So being able to identify these quickly and effectively is something that's helpful. So what could you identify? Where did we start all of these? What did we start all of these with?
Did it find the charge? Bonding type.
There it was. We're looking at the bond. If we can identify the bond, we can start to predict something about the force. What's the bond in sodium chloride? Yeah, we'll stick it with black. We've got an ionic bond. Carbon-hydrogen. You will always hear me refer to it as just covalent, but yes, someone did say it, so I'll go through and write it out too. It is technically non-polar covalent. So you'll continue to learn I'm lazy. I don't like the extra words. What's the deal with our OH bond?
Covalent, polar covalent.
It is polar covalent. How can we identify ionic versus covalent versus polar covalent?
Ionic, there's a formal charge.
So ionic, we might see a formal charge. In this case, we see a formal charge. No, so that didn't work. What's our definition for our ionic? Metal and a non-metal. So if you see a metal in there, you're looking at an ionic bond. What's our definition for polar covalent? What we talked about already and summarized, whenever we have a bond between oxygen, nitrogen, or a halogen to anything else, we've got a polar covalent bond. Well, oxygen to hydrogen, that classifies. What was our covalent bond or our non-polar covalent definition? I'd avoid going anything else. If anything, I'd put polar covalent as the anything else. What's that? Polar covalent is also non-metal, non-metal. Anything bound to itself is by definition a non-polar covalent bond because the difference in electronegativity between the atoms will be 0. And carbon to hydrogen. Okay, there's our carbon to hydrogen, see? Okay. So now we need to come up with different ways to explain these forces. What force do we have in each of these? Well, we said it's differing strength, which means we should probably also come up with differing names. Because you're saying strong force, middle force, weak force, not very cool. Okay, so what names do we want to come up with? I heard of London dispersion, we'll start with that. Okay, our weakest force, you'll hear me refer to as our London dispersion forces. I'll typically also call it just LDF. It's also known as the, that's getting way too fancy for me. Van der Waals is our common one. The other one is our induced dipole, which I don't really want to get into, but I'm pretty sure the textbook does. Is that where you saw it? The induced dipole is technically the better way to reference it. I just think it's more effort than necessary. What other bonds do we, or forces do we have? I want to step away from hydrogen bonding. You are correct that hydrogen bonding is a force. I don't want to introduce that yet. We will start Wednesday with hydrogen bonding probably. Dipole. Where do we get the name dipole from? I mean, London dispersion, Van der Waals. Van der Waals was living in London when he figured it out. I don't know if that's true. Don't quote me. What we're looking at is these partial charges. The way to look at the relationship between those partial charges, we have two of them, right? So we have di, okay? Also known as two poles, a positive and a negative end. We got a dipole. So that OH has a dipole. What's the other one have? Well, it's the same thing, so it also has a dipole. Being super creative, what name do we come up with? We have a dipole-dipole interaction. Okay. Which hydrogen bonding is an example of, which is why I want to step away from the hydrogen bonding. And our last interaction? Last interaction, we're looking at the interaction between, so our covalent one we came up and named after the person it came up with. Our dipole-dipole we named after the names of the structures themselves, effectively. So what do we get for our ionic one? We call it ionic-ionic. That doesn't have the same ring to it, right? picks probably the worst name. Probably worst name after hydrogen bonding. Hydrogen bonding is even worse. Ionic bond. Why is that a problem?
Because it's not a
We're looking at a force versus the bond. The balance between those is very, very sketchy. In some cases, we look at it as a legitimate bond. Some cases, we look at it as a force. What's the issue when it's a force? It's not a bond. Okay? So you have to be very careful with that. One of the other terms that I'm working on trying to actually end up calling it, probably won't happen, electrostatic, which I believe you mentioned earlier, Janine. So electrostatic is also that interaction. Okay? So those are our primary intermolecular forces. There is a fourth, hydrogen bonding, which we'll talk about here. We'll probably start Wednesday with. Okay? So we could look at the balance between all of these. I will start Wednesday on this as well. Come back and fill these in with the definitions on how they interact. Anybody notice an interesting format behind how I've got these organized? Covalent bonds give you what type of force? London dispersion. Polar covalent bonds give you what type of force? Dipole. Ionic bonds give you electrostatic. Noticing that pattern was something that I happened to notice. Propagated it all the way up to a complete circle. Okay? So we'll look over these two slides, and that puts us pretty darn close to the end of chapter 3. So we will be getting into chapter 2 on Wednesday. I doubt we'll clear chapter 2. So 4 will end up getting pushed to next Monday. Okay?